Good morning, everybody, and welcome to the shop. I'm Gerald with Gerald Education. Before we get started, if the material that I put out there is helpful to you and you like it, it would really help me if you liked and subscribed to the channel. Today, we're going to be getting into Newton's laws, actually more specifically Newton's second law. We're going to start a series of solving problems and how to use Newton's second law to solve them. This information will be relevant if you're taking a first year college physics course or if you're taking AP physics in high school. All right, so without further ado, let's get started on some of the problems. Okay, so we're going to solve a couple of problems today using Newton's second law. And what is that law? That would be that the summation of all the forces is equal to the mass times the acceleration. Okay, now keep in mind this is a vector equation, so force and acceleration are actually going to be vectors. Now sometimes you'll see this written without the summation in front of it. All I mean by that is all of the forces added up together, vectorially added up together, is equal to the mass times the acceleration. Now for the problems that we're considering today, the acceleration is actually going to be equal to 0. So let's get into this. Okay, here we go. Consider a stationary mass held in place by two cables, one of which is horizontal. Let theta be 30 degrees. So this angle right here is 30 degrees. And let m be 12. So the mass is 12 kilograms. We'll put that in a minute. And the acceleration due to gravity, little g, we're letting that be 10. Now sometimes that's going to be 9.8. I like to pick 10 when we're going over problems because it just makes the numbers easier to talk about. So let's just stick with 10 for now, but in principle 9.8 would be the same thing, just replace the 10 with the 9.8. So here we go. Now if I look at this mass where this is attached, if I were to draw a parallel line right here, this angle would also be 30 degrees because alternate interior angles from geometry would have to be equal when the lines are parallel. Okay, so I'm making that parallel with the roof that's holding that cable. All right, let's look at this. On the AP exam, if that's what you're taking, they're going to ask you to draw a free body diagram on that dot with the force arrows emanating from that dot. So when you put that in, then generally they'll put it on graph paper or something like that so you have some place to put it. But I'm just going to draw a little axis right here. So here's my y-axis and here's my x-axis, okay? Now, when you draw the free body diagram for the test, they don't want you breaking it up into components. They just want a listing of the forces. So I'll put those in now. So we know we have a force this way, okay? And I'm going to call that T1, and it's at an angle of 30 degrees off the horizontal. We also know that we have a force acting in that direction, okay? And I'll call that T2. That's strictly horizontal. Now, we also have a force acting down that's caused by gravity. Okay, and we'll call that mg. So remember, the force that acts on an object is the mass times the acceleration. So we're going to use the mass of the particle there, if you want to call it that, multiplied by g. So that's the force that gravity is going to apply. Now, if we stick a number on that, that would be 120 in this case, because the mass is 12, as was stated up there, and the acceleration due to gravity is 10 meters per second squared. So 120 is where I'm getting that from. Okay, now it says in this case the summation of all the forces is equal to 0 for us because as far as we're concerned in this one, this mass is not moving, it's not accelerating. So I can say that the summation of all the forces just adds up to 0 because I'm letting A be 0 since it's not accelerating in any direction. Okay, now the objective here whenever you're solving one of these problems is you have to break the vectors up and look at it in the vertical sense and the horizontal sense. Okay, so here's what we're going to break this one up right now. So T1 is the only vector that needs to get broken up. So if I have its component here and I have its other component would be here, but we always draw it from the center of mass, so I'm going to put it there. But whenever you're breaking vectors up, one thing I always like to say is the vector that you're trying to break up into components is basically like the diagonal of a rectangle that wasn't drawn. Okay, so we're really going to look at this triangle right here to find the components. And really that just goes back to right triangle trigonometry. Now, if you haven't seen any of my videos on vectors and breaking them up, go back and look at those videos so that you can see exactly what I'm doing here. Now, I'm going to do it one time here, and then the other ones I'm just going to put in a little bit faster. So watch, here's what I mean. So let's say we call this, say we do this way. Let's call this component T sub x, and this component of T1 would be T sub y. Now, one thing I could, and remember, the length of that vector is just t1. We don't know what it is yet. That's what we're trying, one of the things we're trying to find. So I could say this. I could say that the cosine of 30 would be adjacent over hypotenuse, right? So that would be equal to tx divided by t1. And then when I cross multiply, I would get tx is going to be equal to whatever t1 is times the cosine of 30 degrees. Okay? So let me put that in the picture. So instead of tx there, we're going to write this is going to be t1 cosine of 30. And I'm not going to do the whole argument over again, but ty, which I'm going to write over here, you know, ty is really just going to be t1 times the sine of 30. Okay? Now, since it's not accelerating, the summation, the forces have to be balanced in both directions. And the way I'm going to say that is this. I'm going to say, okay, let's look at the y direction and the x direction separately. If I do the summation of all the forces in the y direction, that has to be equal to 0. So what I have is t1 sine 30 minus 120, okay? The t1 sine 30 is up, the 120 is down, and those are both in the y direction, so I'm only looking at the y direction, and that has to be equal to 0. Or you could just say, I mean, you could skip right to the chase and say t1 sine 30 has to be equal to 120, because I know they have to be balanced since it's not moving. But I think this is probably a better thing to do, write it down in Newton's law, just so you get used to using that pattern. So now, the sine of 30 is a half, so really what I have here is 0.5 t1 is going to be equal to 120 when I add 120 to both sides. And then I divide both sides by 0.5 and I get t1 is going to be equal to 240. And the unit on that would be newtons. So there you go. We've answered one of the questions that we had. We just answered find the tension in both cables. So we just found the tension in that cable and it's 240 newtons. Okay? Now, looking at our picture, I'm going to switch to blue. In the horizontal direction, here's one force, here's the other force. Okay, so we're going to do the same thing that we just did. We're going to say the summation of all the forces, but this time we're in the x direction, is going to be equal to 0, because it's not accelerating that way either. If it were accelerating, I'd set it equal to 12, which is the mass, times a, and try to solve for a, but we don't have to do that in this case. Now in the x direction, I have this. To the right, I have t1 cosine of 30, and that's equal to t2. But remember, we just figured out what t1 was. So now what I can say is I can say that 240 times the cosine of 30, which is going to be 0.866 or 0.866, is equal to t2. So all I have to do now is that calculation and I'll know what t2 is. So 240 times 0.866 turns out to be 207.84, and the unit on that would be newtons. So there you go. We just found the tension in both cables. Okay, now we have another problem that's slightly harder than the last one that we just did. So in this case, the second cable is not horizontal. It's on the left side, but instead of just attaching to the wall, it's attached to the ceiling at an angle of 50 degrees. Okay, so let's go through and analyze this one. All right, now we've already done this part before, so this component here for T1 is going to be equal to T1 cosine of 30. And it's going to have a vertical component here, and we'll call that one T1 sine of 30, just like we did before. Now, for T2, we'll use blue. So in this case over here, this is going to be, for the same reasons that I stated before, this is going to be T2 times the cosine of 50. And then the vertical direction, we're going to have that vertical component be equal to T2 times the sine of 50. Okay, so look at that free body diagram. And remember, now that we've broken those vectors up, we don't really want to use T1 and T2 as they were originally. We want to look at everything horizontally, balance that out, look at everything vertically, balance that out. So let's actually do that. All right, so here's what we would have. We'll go in the y direction first. Okay, so in the y direction, what we're going to do is the summation of all the forces in the y direction is going to end up being equal to 0 because it's not accelerating that way. So in the y direction, here would be the sum of the forces. We'd have T1 sine 30 plus T2 sine 50. And I'm adding those because they're both pulling up. They're helping each other in the upwards direction. The thing that's stopping that is going to be minus 120 in the negative y direction, and this whole thing is going to be set equal to 0, because remember, this right here is MA, and A is 0. So now, when I go through this, the sine of 30 is 0.5, so this is going to be 0.5 T1 plus, now the sine of 50 is 0.766, so this will be 0.766 T2. Then I add 120 to both sides, and that's equal to 120. And now I've got this that I can't quite solve because I've got two things in there that I don't know. But that's okay. Let's go over to the x direction. Okay. Now in the x direction, here's what I would have. The summation of all the forces in the x direction is going to be equal to 0 because it's not accelerating that in the x direction either. And so that would mean, I'm going to scroll up a little bit here. That would mean that T1 cosine of 30, that's pointed to the right, minus T2 cosine of 50, pointed to the left, that's why it's negative, would be equal to 0. Okay? Now, could you have just said that T1 cosine 30 is equal to T2 cosine 50 because I know they balance? Sure. I just kind of want you to get used to writing this out in terms of Newton's law, the way it's stated. So now, here's what we have. Cosine of 30 is going to be 0.866 T1 minus cosine of 50 is this is 0.866. All right, I probably should write the zeros in front of these, but 0.643. We'll round to 3 decimal places times T2, and that would be equal to 0. Now here's what I can do. I can say, all right, well, 0.866 T1 is equal to, when I add it to both sides, positive 0.643 T2. I'm going to scroll up a little bit. So now when I divide both sides by 0.866, I'll get T1 is equal to 0.742 T2. So now what I've done is I've solved it. I'm basically going to solve a system, right? I've got T1 and T2 unknown over here and T1 and T2 unknown over here. And in this case, I solved for T1. So I'm going to take this and I'm going to substitute that in for T1 right there, and then we can solve it. So I have, keep this in pink now, I've got 0.5 times 0.742 T2 plus 0.766 T2 is equal to 120. Now when I add all this up, I get 1.137 T2 is equal to 120. Which means T2 would be equal to 120 divided by the 1.137. And that turns out to be 105.54 newtons. Okay, so now I've got that. Now all I have to do now, let me switch colors so it's easier to see. Now I'm going to take this and I'm going to substitute it back in here for T2. And so now I have T1 is equal to 0.742 times 105.54, okay? And that's going to be equal to 78.31 newtons. Okay? So that means we just calculated the tension in both cables. In the first cable, that turned out to be 78.31. And in the other cable, T2, that turned out to be 105.54. 105.54. Okay? Done.